Hello everyone. In this lecture series, we will be discussing about complexometry, which is an important technique of quantitative estimation of ions in a particular solution. So, it involves complex formation, which has been applied as a technique in chemical analysis since many years. However, the usage of this knowledge is limited since the essential requirements for the use of complex formation are met only by few complexes. So, the requirements for complex formation are: the complex formed must be stoichiometric and should be of a definite chemical composition. That means ratio should be either 1:2, 2:3, but not in decimals or in fractions. It should be of a definite chemical composition. The stability of complexes which have been formed must be high in order to observe sharp endpoints in titration. Titration, which is a quantitative technique to estimate the ions in a particular solution, is based upon complex formation reactions between the metal and the titrant in the quantitative estimations. The third important criteria is that the rate of formation of the complex must be very fast, and then the formation of the complex should involve a minimum number of steps, since increasing the number of steps in complex formation makes the reaction very slow and it enables the endpoint to become very sluggish. During the titration wherein a complex is formed, no precipitation should occur. However, the requirements are not always met fully by all complexes, the biggest obstacle being the involvement of a number of steps in complex formation. Complex formation reactions are studied titrimetrically to analyze the concentration of metal ions in a given sample of solution. Hence, complexometry can also be termed as quantitative estimation of metal ions. So, there is a difference between quantitative estimation and qualitative estimation, as in quantitative estimation we are determining the concentration or the amount of a particular metal ion, whereas in qualitative estimation we are determining whether a particular metal ion is present or not in a given sample. And examples of quantitative estimation apart from titrimetry can include the estimations by weight, like in case of gravimetric estimations, or in case of chromatography, or in case of any other kind of a technique. Whereas qualitative estimation involves the detection of ions in terms of analysis, like in terms of mixture analysis. Coming to the complexing agent which can be used in determination of various ions is EDTA, which is the most important complexing agent. EDTA, which is a polyamino carboxylic acid and possesses a very good ability to form stable water soluble complexes with many metal ions. Its full name is ethylene diamine tetraacetic acid and its trade name is Trilon B. Since it forms very good complexes with metal ions like magnesium and calcium, so it can also be used as a water softener and also be used for the determination of hardness in a particular water sample. It can also be used as a textile dyeing assistant since it complexes with heavy metals easily and enables the dyeing of cloth. This is the structure of EDTA, which is ethylene diamine tetraacetic acid, as there are 4 acetic acid groups over here and 2 amine groups as can seen by the structure. EDTA behaves as a very good complexing agent because its stability constant values have been found to be high with many metals. Considering the overall stability constant, if we compare the formation of EDTA metal complexes with copper metal complexes, then In that case, considering the overall stability constant of copper tetramine complex can be given by the following stability value of 4.4 into 10 raised to power 12. In contrast, the overall stability constant of the magnesium EDTA complex is given as 4.9 into 10 raised to power 8. Y4 in this particular equation determines EDTA anion. As it is observable from the K values or the stability constant values, the copper ammonia complex is more stable than the magnesium EDTA complex. As we can see by the K values, the value for copper ammonia complex is 4.4 10 raised to power 12, whereas for the magnesium EDTA complex is 4.9 into 10 raised to power 8. So it can be easily observed that the copper ammonia complex is more stable since its K value or stability constant value is higher than the magnesium EDTA complex. However, as explained by Jerome, in complexes having more than one ligand attached, the reaction proceeds in a stepwise manner. So, in case of copper amine complex, 4 ammonium molecules are attached to copper to form a tetramine complex. This reaction proceeds in a stepwise manner as shown. If the complex of copper with ammonia is seen, it is found that the formation of copper tetramine is a stepwise reaction involving 4 steps wherein one ligand attaches at a time, and this ligand is ammonia. These are the stepwise reactions which can be observed for the formation of a tetramine complex of copper. The first reaction as shows the hexa-aquo complex of copper combining with 1 mole of ammonia to form the complex where one water molecule is replaced by one ammonia. The stability constant value K1 is given adjoining. In the next step, another molecule of ammonia gets attached and replaces another molecule of water. Similarly, the third step where 3 molecules of water are replaced by 3 molecules of ammonia, and in the fourth step where 4 molecules of water are replaced by 4 moles of ammonia, and the stability constant values are given adjoining as you can see on the slide. The K1, K2, K3 and K4 values, these are the stability constant values for each of the stepwise reactions, are smaller than the overall constant, which is a product of the 4 constants. That is, overall constant K is given as a product of all the 4 stability constant values. Hence, the disappearance of the free copper ion on reaction with ammonia at the end point where copper is to ammonia is 1:4, that is 4 moles of ammonia have attached to 1 mole of copper, will not be abrupt as in case of magnesium reaction with EDTA. EDTA always forms 1:1 complex with metal ions, and this is because EDTA is a hexadentate ligand, that is, it has 6 donor sites, and a single EDTA can satisfy all the coordination numbers of a metal ion, the maximum coordination number of a metal ion being 6, and the 6 coordination sites or 6 donor sites which are seen as in the structure of EDTA are the 2 nitrogens and 4 groups, acetate groups, which can donate electrons. So, coming back to our metal EDTA complex, in case of a copper complex, if ammonia is replaced by a bidentate ligand, it is to be mentioned over here that ammonia is a monodentate ligand where nitrogen is the electron donating group. Then if ammonia is replaced by a bidentate ligand, only 2 ligands are required to satisfy the coordination number of copper, which is 4. As in case of ammonia, 4 ammonia molecules are required to satisfy the coordination number of copper. So if a bidentate ligand will be used, and the example which can be chosen for a bidentate ligand is ethylene diamine. As we can see in this, that there are two NH2 groups where nitrogen are present, and these two nitrogens behave as electron donating groups. So ethylene diamine is a bidentate ligand, and only 2 moles of ethylene diamine will be required to complex with copper, whose maximum coordination number is 4 in this case. Complexes formed by metal ions which are polydentate ligands are called chelates. This word chelates is described or derived from a Greek word called chili, meaning the claw of a crab. This is appropriate for such complexes since the ligand, which is EDTA, grasps the metal ion to form a complex, just like a crab can use its claws to grasp its prey. Discussing about the chelate effect is the increase in the stability of a complex when the ligand changes from monodentate to polydentate form is called the chelate effect of the ligand. This increases the stability of the whole complex. A chelate is a 5 or a 6 membered ring. A chelate having fewer number of rings is less stable because of increase in entropy. Hence, chelate formation helps in increasing the stability of a complex and decreasing the number of steps involved in a particular reaction. This is the structure of the metal EDTA complex. As we can see that the metal is there present as sandwich structure or in between the EDTA complex, and one of the ligand, only one ligand EDTA is used to satisfy 6 coordination sites of the metal, wherein 2 coordination sites are occupied by the nitrogen atoms in EDTA and 4 are occupied by the oxygen atoms in EDTA. As seen in this structure, all the rings in the structure are 5 membered. As we can see in this structure, all the rings which are formed are 5 membered rings. EDTA forms complexes with all polyvalent metal ions and many monovalent metal ions. All complexes contain metal and EDTA in 1:1 ratio, irrespective of the valency of the metal ion. Coming to the properties which are possessed by EDTA, EDTA is a white crystalline powder sparingly soluble in water. It is odorless and is acidic in nature, and this acidic nature is due to the presence of 4 acetate groups. It is non-poisonous and insoluble in acids and common organic solvents, but it is soluble in ammonia solution. This is the double betaine structure, or as we can say, the zwitterine structure of EDTA. Zwitterine means where both positive as well as negative charges reside on the same structure. And as we can see from the structure, nitrogen is carrying a positive charge, both the nitrogens are carrying positive charges, and negative charges are residing on 2 acetate groups because of the 2 dissociable protons in EDTA. The structure shows that only 2 hydrogens in EDTA are strongly acidic, which was found out by the stability constant values of EDTA. It has also been observed by the IR studies that the hydrogen in EDTA form a hydrogen bond between the 2 carboxylic groups. However, there are 2 weakly bonded hydrogens which are released during complex formation. Hence, it is represented as H2Y2 negative, and the 2 dissociable or weakly bonded hydrogens are seen in the structure wherein COO is carrying a negative charge. That means these 2 hydrogens have already been dissociated. During the titration, the 2 H plus ions in H2Y2 negative are released, making the solution acidic and decreasing the pH of the solution, as can be seen by the following reaction, wherein the metal ion reacts with H2Y2 negative, which is the formula of representation of EDTA having two dissociable protons. It gives My, which is a metal EDTA complex, and two protons are released in this process. The complex formation in a particular reaction can be detected by the following manner. If there is a color change during the reaction, if there is a precipitate which is formed during the reaction, or if there is a decrease or increase in the pH of the solution. These criteria indicate that a complex has been formed on a particular reaction. For example, if ammonia solution is added to a light blue copper sulfate solution, then the color of the solution changes to deep blue, indicating the formation of the tetramine complex. Similar types of observations can be noted for nickel ion or cobalt ion also. Now, the endpoint in EDTA titrations can be detected by various visual indicators. So, visual indicators are used to determine the endpoint since they give a color change towards the endpoint. In acid-base titrations, pH sensitive indicators are used as protonated form of the indicator differs from the unprotonated form. In EDTA titrations, PM sensitive indicators are used since they tell at which point the metal is attached and when the metal is released from the EDTA complex. PM indicates the metal, pH of the metal. The basic principle behind EDTA titrations is that the metal indicator complex is weaker than the metal EDTA complex, and in this way the reaction will proceed towards completion, because initially the metal indicator complex is formed, and then when the titration starts with EDTA, then since the metal indicator complex is weaker, so the metal indicator complex breaks and EDTA starts forming complex with the metal, since the metal EDTA complex is stronger than the metal indicator complex, which forms the basis of the titration. During the titration, free metal ions first complex with the indicator. When the titration starts with EDTA as the titrant, the metal indicator complex starts breaking and the metal EDTA complex starts forming. This continues till all the metal indicator complex has exhausted and the metal has completely complexed with EDTA. This has happened because the metal indicator complex is weaker than the metal EDTA complex. In EDTA titrations, PM sensitive indicators can also function as acid-base indicators if the pH of the solution is not maintained. And as we have seen earlier, that the pH of the solution will constantly decrease during the titration because of the release of H plus ions from EDTA. So, the pH of the solution needs to be maintained for the PM sensitive indicators to work. There are certain properties which should be possessed by an indicator used in EDTA titrations. The first property tells us that the color change provided by the indicator should be sharp. Then only we will be able to detect the endpoint and tell how much exact amount of metal is present in the solution. Second point says that the indicator should give a persistent color change towards the endpoint. That means the color change should be a permanent color change which should remain for some time, so that it can be easily established that how much amount of EDTA has been used and how much amount of metal ion is present in the solution. Third point which indicates the properties of indicators is that the metal indicator complex and the metal EDTA complex should have observable color difference. Then only towards the end point one can determine that the color change has taken place and the titration is now complete. The indicator should form a fairly stable complex with the metal, otherwise it will dissociate prematurely and a sharp color change will not be observed towards the end point. So, if the metal indicator complex breaks as soon as the complex forms, then by the titration occurs, the indicator, the color change will not be very sharp and one will not be able to observe how much amount of EDTA has been used in the titration and how much amount of metal is present in the solution. Another property which explains this is the metal indicator complex should be weaker than the metal EDTA complex, otherwise EDTA will not be able to break the metal indicator complex and the reaction will not proceed. The reaction between metal indicator complex and EDTA should be a fast reaction to enable to locate the exact end point of the titration. Thank you.